New York, and looking forward to having you in person.
Great. All right. Well, thank you all for coming, and thank you, Laura, for the invitation. It's so wonderful to be here with you all today. And I'm very excited to tell you about this joint work with Ben Briggs, who's a postdoc at MSRI, and Josh Pulitz, who's a postdoc at the University of Utah. So this is a project we've been working on for a long time. I'm going to tell you a little bit about a published, some results from a published paper we have, but I'm mostly going to be talking about ongoing work. So new things that we're still working on. And the main purpose of my talk is to tell you what are these cohomological support varieties in my title. And really, I'm going to try to tell you a little bit of why I got excited about them, why I'm interested in them. And I hope you by the end, you also think they are interesting. So just to give you a bit of context of what's going to happen, the main idea is that I'm going to fix my favorite ring, and I want to study the modules or even the complexes over that ring. And so to each module or to each complex, I'm going to associate a variety that somehow is going to encode cohomological information about the module or the complex I want to study. And I should say, to me, the word variety means an algebraic set, right? So I do not mean irreducible when I say variety. Later, I'm mostly going to be interested in how these cohomological support varieties give me insights into the triangulated structure of the derived category of R. So it's a very cohomological, very categorical thing that I want to do. But I will tell you what all these things mean. Don't worry if there's I just said some unfamiliar words. But I do want to start out by just setting up some technical notation. So throughout all my talk, all my rings will be either local or graded. So I'll fix some algebraically closed fields. And whenever I say R, I either mean that I took a polynomial ring over K, I took a homogeneous ideal, and I took a quotient, or, and this is sort of a choose your own adventure type of deal, right? Everything else happens in both situations, so you choose your favorite. The other option is that I'm talking about some Navarian local ring, and I want to think about a minimal Cohen presentation for it. So this Q is some regular ring, and the quotient is the completion of R. So maybe before I give you a definition of a cohomological support variety, let me say a few words about history. So these were first defined by Avramov, inspired by some work of Quillen, and then later by Avramov and Boukweitz. So this is late 80s, early 90s. David Jorgensen gave a definition. So, okay, I should say this original definition of Avramov, and then Avramov and Boukweitz was only over complete intersections. But then Dave Jorgensen took that definition and extended it to any ring. Now, in recent years, Josh Pulitz, so one of my collaborators on this project, he has been doing a lot of work establishing the theory of these general cohomological support varieties. And he's, as you might guess, the person who got me excited about these things. Now, there are many, many people who have been involved in the story of support varieties. So I want to mention some of them. I'm sure I'll forget some that are important, but in particular, I should mention, among people who've either helped establish the theory or have used support varieties as tools, that includes, Jorgensen, Avramov, Boukweitz, Pulitz that I've already mentioned, but also people like Burke and Walker, Iyengar, and in the non-commutative setting, Negron and Petsulva. So I should say, to me, rings are all commutative, right? But there is a non-commutative theory of support varieties. So I'm going to give you our first definition of support varieties. And then later in the talk, we'll give a second definition. So remember that I have this ring R, and the ideal I is always going to be the defining ideal of of my ring. So I want to come up with a set of generators for I. So this is a minimal generating set. And I'm going to use that minimal generating set to define, of the defining ideal, to define the support varieties. So first of all, a silly note, right? I mod mi is a K vector space of dimension n, right? It's the K vector space that is sort of determined by these n generators. My support varieties are going to live inside of this K to the n, okay? So what is the support variety of M? Maybe I'll write it for a module, but the definition is the same for a complex. But for the purposes of today, I'm really going to mostly be focusing on modules. So these are points A1 to AN inside of K to the N. I'm going to do the following. I'm going to look at my old regular ring. So remember, this is either the polynomial ring or just that minimal Cohn presentation. And I'm going to look at my generators. And I'll use these elements in K, these AIs, as coefficients. So I'm going to make this particular minimal generator of my ideal. And I'm going to think about the hypersurface that it determines. So in fact, for later, let me tell you that since I'll need this hypersurface, I'll need to refer to it sometimes. If I ever say QA, I mean the hypersurface determined by that point. So what I want to know is the projective dimension of my module, is that infinite over this particular hypersurface? And now I'm going to sort of artificially, So a point that is definitely not in here is 0, right? Because Q is regular, so the projective dimension will be finite. But I will artificially add in the point 0. Okay. So a first comment, note that if I choose a particular point A and I compute this hypersurface, and if I then take my favorite non-zero constant and I multiply all the A's by that non-zero constant, that doesn't change this hypersurface that it determines, right? I just multiplied the defining thing by a constant. So what I'm really telling you is that if you take a line through the origin and you take 2 different points on that line, whether one of those points is in here or not is the same as saying whether the other point is there or not, right? So at the end of the day, this thing we just defined is a union of lines through the origin. And as I claim in the beginning, one can show this is actually a variety. So if you like, it's a conical variety. Or another way to view my comment is that I could have defined this cohomological support as a projective variety instead, right? And it would be completely equivalent. But maybe I'll think of this affine description today to make it easier for us, but they're equivalents to each other. Well, I will try to give you some reasons to care about these, but even before I give you any reasons whatsoever, maybe you have reasons to care about finite projective dimension, right? And you're wondering about all these different, your quotient of Q to R factors through all these hypersurfaces. So you're wondering what hypersurfaces is your module, does your module have finite projective dimension over? So even if, for any reason you care about finite projective dimension or not, if you knew how to compute such a thing, you would have access to lots of information. Now, let me give you a few examples of what these varieties can look like. And in a way, that's one of the big questions I want to ask is what shape do these varieties have? So a first easy example is that as long as you have, so remember, n is the number of defining equations. So as long as I have at least one equation, the ring I just defined is not regular, right? Because I said that thing was a minimal presentation. So for sure, if I construct the support variety of K, well, for any A that you choose, I guess I should say for any non-zero A, but remember then 0 is put in there artificially. All these hypersurfaces I'm talking about, they're always singular. They're never regular, right? And so by, Ausländer-Buchstaben, which is one of my favorite theorems, the projective dimension of K over all these hypersurfaces is always infinite. And so, in fact, that tells you that this support variety is full. It's everything. It's the whole space. Okay. Here's a more exciting example. And I won't fully compute it. I'll make some claims and leave it as an exercise. But just to show you the sort of shapes you might see. So a support variety might be full, was what the first example said. Now, imagine that I took this nice, simple, complete intersection. And now let me think of some module over this. So for example, I'm going to take the cyclic module defined by x minus y. If you go and compute the projective dimension over all the different hypersurfaces you might consider of this module M, there's two options. Either you took a point that it's in the line x plus y is 0, in which case the projective dimension will be infinite. So this is the part that's an exercise. Or if you're not this point, take anything else. Sorry, if you're not on that line, take anything else. The projective dimension will be 1. So this tells me who is the support variety of this module. Well, it should be the points that determine this line over here, right? So at the end of the day, it's the line, that I already said out loud what it is, although I said with an X and Y. And so if you like a picture, it looks like this. So it can be full, it can be some of your space. I guess in this case, it was really nice, it was linear, but I'll tell you later, they're not always linear. But that's a more exciting story for later in the talk. They can also be empty. So here's what I think is a really beautiful theorem of Josh Pullett's. This is in fact part of his PhD thesis. So Josh proved that if you compute the support variety of the ring itself, so you're asking over which hypersurfaces is my ring a module of finite projective dimension, right? He showed that that is equivalent to saying that your ring is a complete intersection. So here when I say CI, I mean, that I have a complete intersection. So if you like, I mean that I is generated by a regular sequence. Or if you prefer to think about this geometrically, I mean that the minimal number of generators of I, which is that number I keep calling n, that's the same thing as the height, right? Or if you like, the codimension of the usual variety that I defined, right? Not the varieties I'm talking about. Okay. So, to me, the easiest rings in the world are regular rings, right? And the next thing, maybe the next thing would be a hypersurface, or more generally a complete intersection. So this is saying you being a complete intersection means you have the smallest possible support variety. And if we're not a complete intersection, you always have something else, some interesting support variety. So there is in particular a hypersurface over which you have infinite projective dimension. Okay, what are these things good for? Well, some applications include, and first I'm going to mention one that is more for curiosity. I won't talk about it at length, but this is maybe one of the first applications of support variety in the old complete intersection setting, was that when you have a complete intersection, this support variety for some module is going to contain information. So somehow you can read stuff about either the Bass or the Betty numbers. of your M. So it does, this is the sort of thing I mean when I say contains homological dimension. Now, I won't tell you precisely what that information is, but I'll tell you a sort of theorem that you can prove. So here's a theorem of Avramov and Buchweitz. They show that if R is a complete intersection, and you have two modules of two finitely generated modules, imagine they're M and N. And suppose that if you go high up enough, your X vanish. So eventually you have vanishing of X. Then that's equivalent to eventual X vanishing when you switch the order of the modules, which is sort of fantastic, right? These are two completely unrelated X, but the eventual vanishing in one order is equivalent to the eventual vanishing in the other order. So this sounds like a statement that has nothing to do with support varieties, but the way you prove this is by considering the support varieties of M and N. Now, there are other applications of this sort where you get information about Betty or Bass numbers. And just to say something out loud quickly, very recently, so Josh Pulitz, Ben Briggs, and Daniel McCormick, they posted a paper on the archive just a few months ago. You can go check it out there. Where basically they use support varieties to prove something about Bass and Betty numbers. Maybe I'll stop there. If you're excited to find out what it is, maybe you can check the archive. That's just to say that's one possible application. But I want to talk about a totally different application. I want to talk about what I sort of foreshadowed in the beginning, that I can get information about the derived category of R. And what is that? Well, I like thinking about complexes of our modules. And so I'm not going to get into any technical details. So I'm going to, maybe lie a tiny bit on the technical details. Okay, lie is a strong word, especially for a recording. What I mean is, I just want to give you a basic idea of what this triangulated stuff is, and I don't want to get into any technical details. But the idea is you want to think about complexes of R modules, but you only care about them up to quasi-isomorphism. So you sort of glue quasi-isomorphic complexes together. Think of them as the same thing. Now, inside of this, there's those complexes that have finitely generated homology. So I'm skipping words here. I'm just saying, among these, consider the ones of finitely generated homology. And sort of the way that these complexes of finitely generated homology fit inside all the complexes, it kind of mimics the way that the finitely generated modules sit inside of all the modules. When you want to study a ring, you might be interested in studying the behavior of its modules. You might be interested in studying the category of all finitely generated modules. But there's also a sort of analogous study where you instead study all the complexes of finitely generated homology, and you sort of get analogous type of information. So so this is a category that has a triangulated structure, and maybe I won't define what a triangulated category is, but if you'll understand what I mean. But somehow the triangulated structure of this category gives me even ring theoretic information about R itself. So here's the sort of things that one considers. So first of all, let me point out that I said I'm talking about modules today. I think about a module as a complex, right? I think about the module M as the complex that sits in degree 0 with M, and then there's zeros everywhere else, right? That's what a module is to me. And one thing we're interested in is how we build complexes from other complexes in some finite ways. So given now M will be any complex in this category, I want to know what it means for this M. So this is M builds n, and maybe I have to throw in the word finitely. What that means is that I can start from n and obtain n by taking finitely many of certain types of steps that I'm allowed to do. So let me call them 1, 2, and 3, and now I'm going to tell you what 1, 2, and 3 mean. So starting with a certain complex, or even a module if you like, I'm allowed to do the following things. I'm allowed to take shifts, meaning any complex that I obtain from one I already have by just shifting the homological degrees is now an allowed complex, one I can get to, okay? I'm also allowed to do direct summons. So if I have a direct summon of something I've already constructed, that thing is now constructed as well. And now finally, this is the most interesting of all, is that I can take cones. So roughly speaking, the idea is, suppose I have a short exact sequence and that you've already constructed 2 of the things in that short exact sequence. Then you can build the third one. So I'm going to say AM builds N if I take finitely many of these steps, and then somehow I get to N by doing this. So this definition allows me to now create a complex version of things we think about for modules. So for example, what does it mean for a complex to be built from R? So I mean R the ring, right? And I mean it as the complex that is R in degree 0. Well, at the end of the day, one can see that that's the same thing as saying that M is quasi-isomorphic to, because remember, quasi-isomorphic things are the same, saying that's quasi-isomorphic to a finite complex. Well, by which I mean finitely many non-zero things of finite rank free modules. So just a bunch of copies of R in each degree. These, as complexes, these are what are called perfect complexes. When I think of them in this world of this category, I say that M is small. And you should think of this as secretly meaning sort of like finite projective dimension. You know, so if you have a module of finite projective dimension, you know, module is always quasi-isomorphic to its finite free resolution, right? So you could replace your module by its finite free resolution, which is a small thing. So small kind of means finite projective dimension. And so in fact, that analogy is so strong that we can now rewrite one of my favorite theorems that I've mentioned once today in this context. So the Auslander-Buchsbaum-Sayre theorem, the one that tells me that a ring is regular if and only if every module has finite projective dimension. I can now write it as a more mysterious sounding statement about this category. This is actually the statement that every complex of finite length, finitely generated homology is actually small. So it's small, which remember means it is built by R in this finite way. So you might remember earlier, I told you this characterization of complete intersections by Josh, and I said something like, you know, I sort of alluded to this theorem. I'm now going to tell you that, in fact, Josh also proved a different characterization of complete intersections that sounds a lot like this one. So earlier I said, to me, there's regular rings first, the easiest, and then complete intersections right after. So if I'm going to write a version of this theorem that says R is a complete intersection if and only if something, I should come up with whatever is the next best thing after being small. And the next best thing after being small is being proxy small. So, and you forget what, if you forget throughout the talk what all these names mean, Like small is like finite projective dimension. Proxy small is almost don't have finite projective dimension, but you're close to something that does. So if I like start writing quickly, I might write PS, and now you know it's that funny thing that I defined that we need is proxy small. So what is proxy small? Maybe you don't have finite projective dimension. Maybe you're not small, but you build something that is. So there exists a P that is small, which is a way to say there's a P I built from M that I can also build from R, right? So building it from R means this guy is small. And then there's a technical condition that I'm going to write. You know, it doesn't really matter, but I don't want to be lying, so I'm going to add this technical condition. I just want the supports to be the same. So this is support in the sense that you think it is, not the support varieties I'm talking about. You know, it's the prime ideals that when you localize, you get something non-zero. There's a version of that for complexes too. So anyway, being proxy small, the idea is that you build something that is small. So you're finitely many steps away from actually having finite projective dimension. And so a theorem of Josh Pulitz, this is, I guess, officially 2020, this was in his thesis, so from a couple years before this, is that R is a complete intersection if and only if every complex of finitely generated homology is proxy small. And to me, this is the you know, a new version of Alcindor-Buchsbaum-Serre, but for complete intersections. There is, however, something missing in this equivalence, in my opinion. Something missing that I would love to find, which is in the regular setting, you know, there was a statement about modules before there was a statement about complexes. And here I didn't write a statement about modules. I just wrote a statement about complexes. So in particular, notice that if R is not a complete intersection, then there is a complex that is not proxy small, that kind of witnesses the fact that this ring is not a complete intersection. But is there a module that does that? And that's the thing we're going to talk about. So is there, so I guess let me say, if R is not CI, is there an actual module, a finitely generated module, such that M is not proxy small? And even better, can you do that in some canonical way? Because by the way, you might remember in the regular setting, it's sufficient to look at K, the residue field, right? That guy is finite projective dimension if and only if you are regular. Let me add a couple more comments before I go to the question. Let me add a couple more comments about the theorem. You might know that, you know, this beautiful theorem of Alcindor, Serre, and Buchsbaum, this solved the famous localization problem, right? The problem that said, if you have a regular local ring and you localize it a prime, must you get a regular local ring back? And that problem is really difficult to solve, but it's really easy. In fact, it was an exercise for my students this semester. It's really easy to solve that problem if you know this theorem, the old version. Okay. So the localization problem for complete intersections is even harder. So if you're a complete intersection and you localize at a prime, do you have a complete intersection? That's a really difficult problem, and it was solved by Avramov using, you know, very difficult techniques. But now this theorem of Pulitz gives a new way to solve that localization problem, because now it's a statement you just want to, you know, say that all the complexes are proxy small, and then that's a statement that localizes well, in the same way that having finite projective dimension localizes well. So that's one cool thing about this. I'll also say that one of these implications is easy. The implication that over a complete intersection, all the complexes are proxy small That was operating the work of Dwyer, Greenless, and Iyengar. By the way, I see that there might be something in the chat. I didn't think to open it before. Should I answer anything from the chat?
No, it's already resolved. Thank you.
Oh, fantastic. Sorry, you're also welcome to stop me and ask questions out loud if you want to. Sorry, I wasn't I'm now teaching online again, so I forgot to look at the chat blinking box. Okay, all right. If there are any questions, you can't stop me. Just to repeat that. Otherwise, I'll continue. Okay. So where was I? This was now the perfect time to tell you about the question. And we are recording, but whatever. I'm going to tell you this joke. So I prepared my notes for this talk, and I showed them to Josh, just to take a look, have any comments. And I had written on my notes the same thing I'm going to write now. I had wrote bad guesses. And Josh said, I don't think they're bad. I think they're very good guesses. They just happen to be wrong. And he's right. So these are very good guesses for answering this question, right? So I want to find, when I don't have a module, a ring that's not a complete section, I want to construct a module that is not proxy small. And these, I think, would be your first guesses as to what the answer is. Okay. So first bad or very good guess, but wrong, is K, right? The residue field. In the regular setting, that's what tells you if you're regular or not. Maybe that tells you if you're completing a section or not. But K is always proxy small, whatever your ring is. Being proxy small means you build something that is small, that is finite projective dimension. Well, that you build, let's say, a perfect complex. So a finite thing where you have just free modules everywhere. And the reason, it's not obvious from anything I said, but it's a fact, is that K builds the Cazul complex on a generating set for the maximal ideal. And the Cazul complex is a perfect complex, a small thing. So it always, for sort of trivial reasons, is always proxy small. So it's not going to tell you anything. Okay. The other obvious bad guess next, or very good guess, is you might know this really beautiful theorem of Ben Briggs. So our other collaborator in this project. Which I guess is now officially a 2021 theorem. This was a conjecture of Vasconcelos from 40 years ago that Ben just recently solved completely. And the theorem is that R is a complete intersection. So here's another characterization of complete intersections. If what is called the conormal module has finite projective dimensions. So remember, I was the defining ideal of R. So this is now some module over R mod I. And so it sounds like this conormal module tells you if you're a complete intersection or not. So maybe you just want to prove that that's not proxy small. But sadly, this conormal module may be proxy small. So sometimes it is proxy small over non-CIs. And now I'm going to say just quickly, and I can explain more at the end, maybe for the experts, I'll say why. So if your ring has an embedded deformation, then it always has, this conormal module always have the free summons. And I know it's a lot of new things, but if you remember, I can take summons. Like if I can build summons finitely, right? So if you have a free summons, in particular, you are proxy small because a free summon is a small thing that you build. So that's unfortunate. So this is not the right thing to look for. But I think it just makes the story more exciting, right? Where are we going to look? And I wish I could tell you that we had a sort of canonical place to look. And over the, I was really hopeful at first for a canonical module, and now I'm I'm convinced that maybe there isn't a canonical thing to look for, but I can tell you that when we can find this module, there are many modules to choose from. So it's still good news. Now, we haven't solved the problem completely, but we have solved it for many rings, I claim. And by the end of the talk, it will be clear, I think, some of the things we know and don't know. But I have never seen a ring for which I can't solve this problem. We have a strategy for solving the problem, and I've never seen a ring where I can't somehow apply the strategy, but I cannot prove that I can apply it to every ring. But we can apply the strategy to many rings. So here's a theorem of ours. This is the one from a previous paper. So this is the old stuff that I had to tell you about. So this is joint work again with Ben Briggs and Josh Pulitz. I can phrase it in many ways, but maybe today let me say that R is not CA&AG. And remember, my goal is to find the module over this ring that is not proxy small. So I'm going to tell you some of the sufficient conditions for our theorem to apply. There are others. One thing that I can do is I can solve the problem if R is what we call equipresented. So what is an equipresented ring is that that defining ideal, those F's that we were talking about, they're all in the same degree, or in the local setting, they're all in the same, they have all of the same ematic order. So things like x squared, xy, that's equipresented, but x squared, y cubed is not equipresented. Another situation where we can solve this is if you go and compute the support variety of R. So I know it's not 0 because the ring is not a complete intersection. If it is full, so if it is the whole space, then we can solve the problem. We can also solve the problem if the span is the whole space, which can happen without this being the whole space. So this is not a vector space, but it lives inside a vector space, right? And lives inside Kn. So I'm going to take the span of this subset of Kn, right? The K linear span. So for example, if you have the union of two different hyperplanes, then this will happen. The span will be everything. And there are rings where that happens. So what's the theorem? If I'm in one of these circumstances where I can solve the problem, then we proved that there exists a finitely generated R module that is not proxy small. But we didn't just prove it exists, we gave a recipe to construct it. And in fact, you can take such M if you want to. You can take a quotient of R, so a cyclic module, and not just any quotient. You can take a quotient that is an Artinian complete intersection. So the old theorem, like there was this point 4 that I never wrote that I think maybe we all know, that the ring is regular if and only if K has finite projective dimension. So I guess I'm writing this in the local setting, but there's also a global statement that would be all your quotients to fields have finite projective dimension. Now, to be a complete intersection says that all your quotients to Artinian complete intersections must sort of have finite projective dimension, right? That's what this theorem says. And so really we construct these very explicitly. In fact, even for very complicated things, I have an algorithm and a computer that can write down what they are. And let me tell you very quickly what the main points are. The main points are 2 facts by Josh Pulitz. So in his work establishing this theory of support varieties, is that one of them, if that M is proxy small, and we were looking for things that are not, then the support variety of R is contained in the support variety of M. But remember, if R is not CI, Josh proved that the support variety of R is not 0. So the idea is you're going to find a module whose support variety is kind of too small to contain the support variety of R. That is already not 0. Okay. So there are many things that go into this. But for example, one idea that helps, one thing we prove is that we can always find a module, in fact, a module of that type, right? One of those cyclic guys that it's Artinian and complete intersection. That we can always do for any ring. You can always find such a thing where this is contained in a hyperplane. And so, for example, if your support variety is full, you find the module whose support variety is contained in a hyperplane. So it can't contain everything. So then you're done, right? And if your ring is equipresented, the idea is the way that we find these things is these modules we find in these hyperplanes, they're sort of determined by minimal generators of I, by those Fs that have minimal degree or minimal order. So if everybody's of the same order or degree, then you can kind of go in all directions is sort of the idea. So if you can go in all directions and this isn't 0, then necessarily something, one of those things contained in a hyperplane of whatever direction you want, one of those will not contain this. That's kind of the idea. But this old work of ours, well, not that old, but this first project got us really excited into understanding what does this look like, right? What can the support variety of a ring be? Because if you start computing examples, one thing you'll notice is that this happens very often. And so we really wanted to understand, maybe these are always big in some sense, right? What kind of shapes can these have? For a long time, we thought these were always unions of linear spaces because all the examples we had, and we had many, were all of that kind. That's false. And it took us a long time to find a kind of example to that. But the thing that has helped us in recent years, in our more recent work, we've now proved things like this. So trying to understand the shape of these things, we can prove, for example, that if R is Goolage, then the support variety is full. Now, maybe you haven't heard of Goolage rings, and maybe I'll stop myself from giving you a proper, pretty definition, but I'll just say quickly, there's a condition on the Poincare series. The Poincare series of whatever ring you want has some upper bound. And if that upper bound is achieved, then your ring is Goolage. Another way to say this is if you know what the homotopily algebra is, if the homotopily algebra is free, that's equivalent to your ring being Goolage. But maybe the more interesting thing that I have to say is that in some sense, in some precise sense, many rings are Goolage. And so that kind of explains why we were seeing many examples of this kind. And so in particular, notice that in this setting, then we know how to solve the problem. And I should say, if R is Goolage and not CI, right? Then indeed, this is true. And not a hypersurface. A Goolage ring is only CI if it's a hypersurface. But anyways. So in my last 5 minutes, I want to tell you how is it that we can prove things like this? And how is it, so for example, one thing we can do is we can compute support varieties with a computer. So with Janina Letts and Josh Pulitz, we're writing a Macaulay 2 package that's almost ready modular documentation that you can obtain online. It is available. You can find a link to it from my website. So we're writing a package for Macaulay 2 that will compute various things related to, that does compute various things related to fixed subcategories. And in particular, it computes support varieties. And the key to being able to do all those things is, remember I give you a first definition in the beginning. Now I'm going to give you a second definition. So with Josh and Ben, we have defined a new theory of support, cohomological supports, that is the same as the old one in all the settings we've been talking about before, but it's a different construction. And so in particular, it allows you to compute support varieties in a really nice, simple way, in particular with the computer. So this will look terrifying. I pre-wrote it so I could just point to things, just to give you I'm not trying to tell you what the definition is necessarily today. I just want to give you a sense for what it looks like. Okay, it's a construction for computing this support variety by Ben Briggs, Josh Pulitz, and myself. So the idea is the following. I'm now going to think about any quotient, any map. So our Q is no longer regular. This is any local or graded map that I like. Of course, you can also extend the old definition to any local or graded map in sort of an obvious way. So you're going to think about the kernel of that map. That's your new I. And the idea is you're going to do the following. You start off with your X over here. And now X is the thing I want to think about. First, I find a free resolution for it over Q instead of over R. Then I find a system of higher homotopies for these. Don't worry about what the definition is. The very basic idea is you start off with the multiplication maps by your generators, and you find null homotopies for these. I guess you really start from taking the differential, okay? And then you're going to construct a sequence of maps that are indexed by tuples, where the entries in the tuples are as many as generators you have. And then you build something. And I will say very, very fast for the experts that if you know what a system of higher homotopies is, this is not your usual system of higher homotopies. There's an added condition that is necessary for complexes to make this all work. But anyways, you construct something that you can construct, that your computer can construct. It always exists. And then you take these maps that were indexed by tuples, and you're going to sort of add them all together in some fancy way with some monomials. So think of these A's right now as variables, but later they will take the role of the, the point that you want. You later like plug in values for points. And then you're going to construct, so M, remember, M was the resolution that I came up with. So I take this resolution in my calculation, and you're going to break this resolution into even and odd parts, the modules themselves that appear there, or the things that show up. So you separate it into even and odd parts. You take these fancy maps you made, and you're going to end up with this complex. So you really end up with two maps, right? One between the evens and one between the odds. These are coming up from those maps you wrote. So at the end of the day, this kind of looks like you just have two matrices, right, where their compositions are zero in either way that you do it. So maybe this kind of looks a little bit like a matrix factorization of something. And then the support variety is a set of points where that complex is not exact. And whenever you start off with something finite, with something in finite projective dimension, you can very explicitly do this in a computer. And it sounds like it was crazy and very complicated, but actually it is not. It can be computed in like a fraction of a second, for nice enough things. And by having this description, one can then prove. So somehow, lots of things that are very hard to prove with the old construction become easier to prove in this new construction. This new construction, as I said, is the same as the old one for maps of finite projective dimension, but they differ in general. This one is a little finer than the old one, and I'm seeing that it's 51. So I'm just going to write very quickly a comparison between them. So this new theory of support variety can be compared to like the old one, but I guess now for a map, some obvious generalization of the old one. Maybe I'll put a hype to remind us it's that hypersurface thing. And at the end of the day, there are more things that now that one can prove, but I don't have time to tell you those things. So I'm going to stop here, and thank you so much for your time.